So let's do some problems where we attempt to use Coulomb's law to either determine the force between objects, the charge on the objects, or the distance between objects. So here's our first practice problem. So we have one charge of 2 coulombs is 1.5 meters away from a negative 3 coulomb charge. Determine the force they exert on one another. So we have a 2 coulomb charge, a negative 3 coulomb charge that are 1.5 meters away. So I'm going to just kind of draw out this scenario just so I get an idea of what I'm looking at. So I have a positive 2 coulomb charge, I have a negative 3 coulomb charge, and their centers are a distance of 1.5 meters apart. Okay, and I know that when dealing with Coulomb's law, I have the following variables associated with it, where F is the force they exert on one another, K is Coulomb's constant, Q1 is the charge of one of the objects, Q2 is the charge of the other object, and R is the distance between them. So I know that in this scenario I'm looking for the force, so that's going to be my question mark. K is a constant, and it's always going to be 9 times 10 to the 9th Newton meters squared per coulomb squared. Q1 is the charge of one of the objects, and it doesn't matter which one I pick, so I'll pick the 2 coulomb charge to be my Q1. Q2 is the charge of the second object, which in this case is negative 3. Now, I don't necessarily care about the negative sign associated with this, and we'll talk about this in a little bit. So what I'm going to do is I'm going to just absolute value this because it doesn't necessarily matter. Okay, and the distance between the objects is 1.5 meters. So here's my setup. And I know that according to Coulomb's law, F equals K times Q1 times Q2 over R squared. So, with that being said, let's take our values and let's plug them in because I'm actually trying to determine the force. So, here we go. Move this over here a little bit. There we go. F equals K, which is 9 times 10 to the 9th Newton meter squared per coulomb squared, times Q1, which is 2 coulombs, Q2, which we said was 3 coulombs, and the distance between them, 1.5 meters, and that value is squared. So, we put all this into our calculator. So let's go ahead and put my calculator in here so you can see how I'm doing this. So 9 E9 times 2 times 3 divided by parenthesis 1.5 squared close parenthesis. So I get a force of 2.4 times 10 to the 10th newtons. And remember before I said that a charge of 1 coulomb was a lot of charge. So in this case we have a lot of charge, so I would expect my force to be very, very big. Okay, let's try another one. So the next problem that we have to try is this one. And again, we're looking at the force between the objects. So we can go ahead and do this problem as well. So we have a negative charge of 200 microcoulombs and a positive charge of 800 microcoulombs, and they're separated by a distance of 30 centimeters. And we want to know what is the force between the two objects. So again, I'm just going to draw myself a rough sketch so I can quick get an idea of what I'm looking at here. So negative 200 microcoulombs, 800 microcoulombs. The distance between them is 30 centimeters. Okay, and I want to know what's the force. Well, here are my variables for Coulomb's law again. F, K, Q1, Q2, and R. So, I don't know the force. That's what I'm looking for. K is a constant. 9 times 10 to the ninth Newton meters squared per Coulomb squared. Q1 is the charge on one of the objects. So let's say the 200 microcoulombs. And remember, we don't necessarily care about the negative part. The only thing the negative part tells us and will help us determine is if the force is attractive or repulsive. So I don't really care about it, so I'm just going to kind of take it out and say 200 microcoulombs, and then I know that these two things have a force that's causing them to attract to one another, and that force is equal. Okay, 200 microcoulombs, and Q2 is 800 microcoulombs, and R is 30 centimeters. The distance between their centers is 30 centimeters. Now, remember before I said that we have to make sure that our variables are in appropriate units. Microcoulombs is not an appropriate unit. Coulombs is the appropriate unit. So we have to actually convert this. So we're going to convert 200 microcoulombs to coulombs. And the way that we do that is we say that a microcoulomb is 1 times 10 to the negative 6th coulombs. So 200 microcoulombs is 200 times 10 to the negative 6th coulombs. And 800 microcoulombs is 800 times 10 to the negative 6th coulombs. And remember also that distance between objects must be in meters. 30 centimeters to meters divided by 100 is 0.3 meters. So there we go. We're set up. We're ready to go. Let's get Coulomb's law and start solving. So F equals K Q1 Q2 over R squared. Okay, here we go. F equals 9 times 10 to the ninth Newton meters squared per Coulomb squared times charge 1, which we said was 200 microcoulombs, which is 200 times 10 to the negative 6 coulombs, times charge 2, which we said was 800 microcoulombs, or 800 times 10 to the negative 6 coulombs, divided by the distance between them, which is 0.3 meters, and that's squared. So we have this all set up. Pull out our calculator and solve. So let's put it in our calculator. I'll let you see what I'm doing here. 9 times 10 to the ninth times, oh, and I'll actually put this in parentheses, 200 times 10 to the negative 6th times 800 times 10 to the negative 6th divided by parentheses 0.3 squared close parentheses. And I get a force of 16,000. So notice then, between the two objects that we just did, one of them had a very big charge, one of them has a smaller charge. So our force then is smaller when we're done solving. Okay, let's keep going then, because I want to make sure that we do something a little different as well, where maybe instead of solving for force, I solve for the distance between the objects. I like that. So here we go. How far apart? So how far apart, this is looking for a distance, are two charges, one of magnitude 3 microcoulombs, the other of magnitude 5 microcoulombs, if the force between them is 20 newtons. So 3 microcoulombs, 5 microcoulombs, 20 newtons. So draw my little sketch here. I have a 3 microcoulomb charge. I have a 5 microcoulomb charge. These are both positive, so they will repel. And it tells me that the force is 20 newtons, and the force is going to be the same for both, just in opposite directions. And I wish to know what is the distance between them. So R is what I'm going to attempt to solve for. Okay, so let me set up all of my variables here. F, K, Q1, Q2, and R. F I know is 20 newtons. K is a constant. 9 times 10 to the ninth Newton meters squared per Coulomb squared. Charge 1 is 3 microcoulombs. Charge 2 is 5 microcoulombs, and I don't know the distance between the objects. Remember I said that we have to convert microcoulombs to coulombs, so 3 times 10 to the negative 6th coulombs. 5 times 10 to the negative 6th coulombs will be our second charge. So we're set up. Let's get Coulomb's law in here. F equals K times Q1 times Q2 over R squared. Now in this case, I'm not solving for F, so I'm going to rearrange this equation to solve for R. So in order to do that, I'm going to multiply both sides by R squared. Multiply by R squared. So this cancels. And I'm left with R squared F equals K times Q1 times Q2. Then I'm still trying to get R by itself, so I'm going to divide both sides by F. I'm going to divide both sides by F, and that cancels this one out. And I'm left with R squared equals K times Q1 times Q2 over F. Then, since I'm still just trying to get R by itself, I'm going to square root both sides. And the square root is going to get rid of the square on the left-hand side. So I'm left with R equals K times Q1 times Q2 over F square rooted. So there's my equation that I'm going to use to solve this problem. So now I can take my values, plug them in, and solve. Here we go. R equals the square root of 9 times 10 to the 9th Newton meters squared per Coulomb squared times Q1, which is 3 times 10 to the negative 6 coulombs, times Q2, which is 5 times 10 to the negative 6 coulombs, divided by 20 newtons. So let's get my calculator out here. The square root of 9 times 10 to the 9th, 3 times 10 to the negative 6th, 5 times 10 to the negative 6th, question mark, there we go, close parenthesis, divided by 20 newtons, close square root parenthesis, equals 0.082 meters. So R equals 0.082 meters. Okay? Now, let's do one more, because we've solved for force and we've solved for distance, but what we haven't tried to solve for yet is charge. So let's do one more where we're trying to solve for charge, and then I will allow you to just do practice problems to get your feet under you and get better at this. So here we go. A negative 6 microcoulomb charge exerts an attractive force of 65 newtons on a second charge that is 5 centimeters away. What is the magnitude of the second charge? So I have a charge that's negative 6 microcoulombs. I have a negative charge. I have another charge that I don't know. I know that it's an attractive force between them, which automatically, right off the bat, if it's an attractive force, I know that these have to be oppositely charged or differently charged. So if this one's negative, this one has to be positive. I know that right off the bat. Okay? The distance between these two objects is 5 centimeters. And I want to know how much is that second charge. So let's get my table here. F, K, Q1, Q2, and R. F is 65 newtons. It tells me that in the problem. K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Charge 1 is negative 6. Remember, the negative just tells us whether, or just helps us determine whether or not it's going to be attractive or repulsive. So I don't necessarily care. I'm just going to look at the magnitude of the charge. Charge 2 I don't know. The distance between the objects is 5 centimeters. So before we do anything here, we first have to make sure all our units are appropriate. Newtons, good. Newton meters squared per Coulomb squared, good. Microcoulombs, no. So we have to make sure that we convert this. So this would be 6 times 10 to the negative 6th coulombs. Centimeters, no. Divide by 100, this becomes 0.05 meters. And we're trying to solve for Q2. So Here's Coulomb's law, which helps us determine the force between charged objects. And we're trying to solve for Q2. So we're going to rearrange this equation to solve for Q2. So first multiply by r squared. So I have r squared times F equals K times Q1 times Q2. Then, I'm still trying to get Q2 by itself. I'm going to divide both sides by KQ1. That cancels it on this side. Divide by KQ1. So then I'm left with Q2 equals r squared F over KQ1. Now, I'm ready to go. Q2 equals r, which we said was 0.05 meters squared, times 65 newtons, divided by 9 times 10 to the 9th Newton meter squared per Coulomb squared, times charge 1, which is 6 times 10 to the negative 6th coulombs. Calculator. 0.05 squared times 65 divided by, now this whole thing has to be in parentheses, 9 times 10 to the 9th times 6 times 10 to the negative 6th, close parentheses on the denominator, and I get charge 2 to be 3 times 10 to the negative 6th coulombs.